Okay. My name is David Recker, and this is Vaddi. He's from Marvell, and we're both going to share the presentation. I'm going to go through the Circut Boulevard section first, and then I'll hand it over to Madhu after that. Okay? So, we're going to present on putting the SPDK on a open channel SSD. And one of the things that the open channel SSD is supposed to support is give you a better performance when we deal with multi-tenant type of environments. So that's why we're going to give you some data that shows you the performance on these noisy neighbor type of problems. First, I want to give you some background on Circut Boulevard. We are a startup, and we have a lot of experience in flash and storage throughout the years, and we're focusing on developing a fast database and storage system for the enterprise and cloud market. We're also a company that was founded in the summer of 2017, so we're a relatively young company. But our team has been very big contributors to the open source community. So we've been very involved with the Linux kernel, had a lot of input into the Open Channel 2.0 specification. And then we also had a lot of experience working on the Open SSD FPGA, which was used to develop the first spec for Open Channel. And then, of course, we've been involved with the SPDK since the version 17.10. And then our team has also contributed to the RocksDB as well. So we have a lot of experience using the code and providing feedback to the community. So today, we're going to present on, if you looked outside, we do have a demo, and we're presenting on how the SPDK works on an open channel SSD, and we partner up with Marvell. Marvell provided us with a reference platform with a SSD and a controller. And then we worked very closely with the Intel team to get the SPDK. We started this back in January, so we had just a few months to work on this. And as you know, anytime you get new code and you get a new reference line, there's a lot of bugs and there's a lot of work that has to be done. So once we got the proper support, we got this up and running, we got a very stable system. Then we were able to make some measurements, and we could show you the performance that we're getting. And also, we show you an environment where we see some benefits of the open channel. So the other thing, too, is we have our demo right on the other side of that wall. And actually, we've been running that nonstop since Monday night. So we're acting kind of like a QA team for Intel. So it's been very stable, and been running for almost 40 hours now. So our hardware setup, we basically got a Supermicro platform. It has a dual Xeon scalable gold processor. Each processor has 12 cores. And we have 2 slots. Each processor has its own set of DIMMs, so we could expand that in the future. And then we plugged in the OC SSD into the PCI slot. And we configured it for each CPU so that we could do the comparisons. So this supports Open Channel 2.0, and we're using the Marvell 88SS1098 platform controller. And we configured this to be for the NVMe identification namespace, and we programmed the logical block address to have a minimum of 4 kibytes. The other thing we do is we also turned off the metadata size, so we made it 0 so that we can make measurements and we could get full performance measurements. And then we also turned off the hyper-threading as well on the Xeon processor. One thing about Open Channel is that it allows you to bring out the geometry of the flash so that you could program it from the host processor. So you can see that we have the logical bits that we could use to program the actual physical units. So in the platform itself, we could program up to 8 groups with 8 physical units for each group. And then we have the chunks that are configured up to 1,478 different chunks, and each chunk can support 6,144 logical blocks of size of 4 kibytes. The other thing too is that the platform uses a Toshiba 3D TLC NAND, and the characteristics of that flash, we could actually do a write unit of 96 kibytes, and we can also do a read of up to 32 kibytes. So I think one of the special things about the open channel SSD is that we bring out the geometry. So you can see that we could take the logical block, and then we could access the array of physical units. So the setup allows us to actually access an 8x8 array, and the groups have 3 bits to program, so you could actually access any of the groups right here. So you got 8 groups, and then you have the physical units that are connected to each of the groups. And then we could program it. Each physical unit is broken up into the chunks, which eventually is broken up into the actual logical block. One of the things to note on here is that the current spec supports a write size optimal of 24. So what that means is that you could actually take 24 of these blocks, 4 kibytes, and that's how you get your 96 kibytes of write capability. And then there's one bit of ambiguity right now is on the read side. So the read size optimal is not well defined right now. So we actually put a patch in there to make it work so that we could take advantage of the full capabilities of the NAND. And then the other thing too is that when we do our analysis, we took this array, we programmed to 2 different modes. So the first mode is when we divided up the physical units into 4 different channels. So this is when we isolate the blocks, and we could run some performance programs on that. And then the other case is when we use the full 64 physical units as a single block device. The other thing to notice on this is that, I guess this is important, and any type of NAND flash, the read time is always less than the programming time, and then that, of course, is always less than the erase time. So I think that shows you, keep that in mind when you look at the performance numbers. So now we have the hardware set up, we have the software set up. What we wanted to do is we wanted to take the P block and run that as a baseline, and compare that with the SPDK. The P block was run on the Linux 4.17 kernel, and when we got the platform from Marvell, they provided the patches that allowed it to run in a stable fashion. And then we took the SPDK, we ran that on the 5.0 Linux kernel. And of course, both the Marvell platform and the SPDK are still in the bring up stage, so there's still a lot of work that's being done, and a lot of development that's still being done to stabilize it. We had to take the patch code that was available for the P block and then port that into the SPDK. So you can see that we ported all this functions into the SPDK, got it up and running. The other thing too is that we did create this optimal read size patch, which we contributed to the SPDK Garrett hub. So hopefully that will get reviewed, and then that'll get released into the next release. The other thing too is that we're running a flexible I/O software, the 3.13 version, and this gives us a little bit of flexibility. We could isolate different CPUs within the Xeon processor, and we could isolate it so that we make sure that we're not getting any interruptions, and we run a full throughput, and we could run the full performance on our platform. And then we froze our code in April 9th. And of course, it's a little bit complicated because there's still a little bit bugs that we had. So we had to work very closely with Wojciech in the back and get some fixes that allowed us to fix this chunk right pointer error that we had. And now that we got this up and running, we got it stabilized, we actually ran some performance tests. So the first thing that we want to do is get a baseline code, right? We want to get the baseline to see that our system is running properly. So what we did is we configured our platform to a single block device with 64 physical units. And then we ran 2 full write cycles that are 120K bytes. But we ran this with a single thread with a queue depth of 64. And then we followed this with a read so that we could measure the performance for both the PBLK and the SPDK solutions. So on the graph, we actually have 3 different graphs that are shown on the diagram. So the first diagram with the PBLK in the blue, you can see that the first write cycle took about 1,000 seconds. And for any type of memory subsystem, there's going to be some kind of over-provisioning. So this was set up for a 20% over-provisioning. And we wanted to get the next write cycle so that we could condition the memory. So you can see that the second write cycle, we're kind of writing over to the extra memory that was provided by the over-provisioning. And then what happened here is that we're starting to get erase cycles because we're overwriting the memory that's in the system. Please note that this is still in the bring-up stage, so there's still some work in progress right now to get this more stabilized. But what this diagram shows you is that there's a consistency between the PBLK and the SPDK. And then when we follow the read, so you notice that, remember I said before that the read is faster than the write, and then that is faster than the erase. So this diagram pretty much matches that. So when we ran the SPDK as we received it, the read cycle didn't support that RS optimal feature. So once we implemented that, you see that we're able to get the read data, the IOPS to match or get very close or a little bit better than what the P block was getting. So now we took the performance and we were able to get pretty equivalent values between the P block and the SPDK. Now we can start taking measurements. So after that, we decided that, one of the biggest problems that you see in a cloud environment is that you have a multi-tenant environment, you get noisy neighbor issues. So what we did is we configured the system and tried to do a comparison. So we have the diagrams on the left side. The diagrams on the left basically are the straightforward single block device running all 64 PUs simultaneously. And you can see that when we have applied basically 4 random reads with a random write, even though the memory is partitioned into 4 different partitions, you can see that we are running into this noisy neighbor issue. So the noisy neighbor issue is when you're running a program into different threads. So we have four different threads because we're running the read with 3 threads. And during the scenario, you basically have to wait for the other instruction to complete. So you have a write instruction, you have to wait for that completion before you can start your read instruction, and that's why you get this variance in your performance. So you can see that this is a big issue. This is a big issue if you want to deal with QoS and if you have to guarantee a certain performance to your customer. And if you can't guarantee the high performance, then you can't charge as much. So this is a big issue. So if you look closely, there's some spikes here too, but the data rate's so low, so you can't really see it, but it looks pretty smooth. We ran the same platform with the SPDK. SPDK is still being worked out. There's some issues with the write buffer right now, so that's what's causing these overruns and underruns. So, but you can see that a similar reaction occurs because you have to, the writes interfere with the reads, so you get some kind of a sporadic data output. So there's this is still being worked in progress. I think the Intel team is aware of the issues here. But what's nice about this is once we configure the system into the 4 different channels and isolate the channels and write the different threads into those different isolated channels, we can see that we smooth out the performance. So this simple task allows us to show that not only do we get a more stable performance, we also get a much higher throughput. So now we could charge much higher for this solution. And then we ran the same solution with the SPDK. And with the SPDK, you can see that the performance is a little bit lower, but that's an issue that we have with the driver right now. But you can see that even with the SPDK, we got a very solid QoS and a stable solution. So I think that open channel with the ability to isolate the memory into different blocks allows us to have more control of where we place that memory into the memory, or the data into that memory. And you can see that by doing so, we have much more control on the bandwidth. So out on the hallway in our demo, we're actually showing this performance between the SPDK and the non-isolated memory and the isolated memory. So the team is continuing to do work, and they're still involved with the community. We're doing a lot of contributions to the Open Channel SSD 2.0 spec itself. We have some code that we've submitted, and that's being reviewed right now. We have a couple issues on the FTL. The first issue was this, the read size optimal that we saw that doesn't take advantage of the memory. And you can see that the next one, this was the chunk pointer issue that we submitted, and then we had an initialization error for the erase. The other things that we're working on too is the team is very strong at supporting the next generation of features. We're looking into the bottlenecks that we saw with the performance on the SPDK. We're also going to work with Marvell to get asynchronous namespace management, NAND management. And we also believe that another aspect that has an impact on the performance is the CPU affinity. So one of the things that we've done is we run the code on a 12-core Xeon processor, and by running the code on different processors, we could get much better performance. So we have some work to do there. And then when we get the PMDK and the ZNS support, we'll also provide that into our platform and work on that. So I also wanted to kind of acknowledge some of the people that helped us to get this platform up and running. Wojciech from Intel helped us a lot. We had a lot of issues that we had to work through. Matthias is famous for starting the open channel specification, and we worked closely with him on the kernel. And then we had great support from the Marvell team for the firmware and the bring up on the hardware. I also wanted to show you this kind of a history and roadmap of the open channel development. The team that we have from Circut Boulevard actually had experience, and they actually worked for a different company that developed the Jasmine reference design. And this was a reference design that kind of initiated the whole open channel concept. And as Intelex was a company that got acquired, so when they started working on the open channel, they moved to the Cosmos platform so that they could actually program the FPGA and get better results for the open channel. And then that eventually moved to the specification to be released in 2015. as the open channel became available for the public, in 2018 there were two major companies that actually committed to developing a project. So Alibaba and Microsoft, they created internal projects to port open channel to their internal projects. And I don't know where the state of those programs are right now, but I think that there is some activity. And then in 2019, we worked with Marvell to come up with a platform here. We're also working on a reference design that we want to make available to the open channel community, so that it'll make it a lot easier to have a real set memory SSD that people could program, and then it makes it easier for them to contribute. So we'll have a new reference design in the second half of this year. So, and that's going to be in the U.2 form factor, so that it should be able to plug into any of your servers. And then, we're working on our own project. We call it the Cinebro. So the Cinebro storage appliance is basically architected like this. We're going to have a server box that we could plug in any type of a DIMM card. So when we get the PMDK and we get the Optane cards, we could just easily plug that in. And then we'll have the different SSD cards that we could plug into the ruler slot here. So we'll provide a full software stack and a whole entire appliance that they could plug into any cloud or enterprise box. So long as we support the form factor, this is our box, but you're talking about the reference design?
Oh, yeah, I just wonder if there were any restrictions or limitations on the types of SSDs that fit in Cinebro.
Yeah, I think we could customize that. So if you want to use different type of NAND processors or SSDs, we could customize that to your solution.
How many Optane DIMMs can you put in there?
So I think this processor can support up to 8 DIMM cards. Okay. And I think, in a short period of time, we were able to demonstrate that we do have a solid solution that works with a SPDK. It's running for over 40 hours right now, and it's stable. There's still some work that has to be done, but we've been able to demonstrate that open channel is a good, has a lot of promise in solving this issue with the noisy neighbor environment. So I think that we're going to continue working on that. We will have the reference platform by the end of this year. So if you have any questions or you want to have some quotes or additional information, please write us at info@circuitboulevard.com, and we'll provide you with a quote, and we'll provide you with a schedule as well. And with that, I'd like to introduce Madhu, who will continue with the Marvell section of the presentation.
Thank you, David.
All right.
Thank you, David, for all the details and lots of information about whatever work we have done so far. So I think David covered most of the important part, what we have done in SPDK demo. So I'm going to cover a little bit about our controller, what kind of capabilities we have in our controller, and also what we have done in our prototype work. So coming to our controller, it's like 8 channels, and then we can support until 16 terabytes, almost like 128 dies. It can go up to all the capacity is usual, like 16 TB, 16 channels kind of stuff. And it's a PCI Gen 3 and single port and dual port. So we do have good enterprise features like virtual functions and dual port, and we have tested everything. It works good. And we do have end-to-end data security like T10 diffDIGs. And also, we do have very good security and reliability modules. And we do have 4 RFID codes if we need to have more flexible firmware design architecture, in each CPU you can utilize, the firmware can utilize in different way. Because some people want 2 instances of the host side, some people want media side 2 instances, 2 FTL instances. So we provide more flexibility for the architecture and design for firmware. So this is a quick look on our hardware capabilities. So coming to performance is, let me start from bottom, and we could reach like 650 decent good kilo IOPs, and that is like 533 MTS speed, 9 interface, and 8 channels, 64 dies, a BIX3 TLC. The chip, even it can go all the way to 740 to 750 if we use the faster NAND and faster interface speed, and we also did tested that. And then random write around 500 kbps, and sequential read and write, we can go all the way the PCI Gen 3 maximum. So this is the important one, which maybe we would like to spend more time here. If you see the diagram here, so what we want to try initially is, we know that the fundamental concept of open channel is the bottom layer of NAND, the different parallel units. So this is where the actual performance lies. Each NAND device can program, can read, can erase independently, right? So we would like to expose these parallel units to all the way to applications, the visibility of these parallel units to application, so that application can utilize this parallelism based on its data nature, its application nature, right? So every application, the purpose and the way the data nature and pattern is different. So exposing all these parallel units to the application makes big difference, so that I/O isolation can be different and it can be much better. And it's like, some of the dies can be used for only program data, some of the dies can be used for very high efficient data, and they can configure TLC or SLC mode. So this all geometry exposing here makes big difference in terms of the isolation and also determinism, like I/O determinism. Of course, many people has a question about, okay, just exposing all these parallel units is good enough to have I/O determinism, may or may not. So still SoC has to provide a good capability internally, kind of decoder or encoders having enough capability, and also scheduling capability internally in this backend control and media firmware. So our work is mainly here in this prototype is, we want mainly to check, our SoC can be compliant to the interface of the OC interface. Because apart from the OC interface, rest of the backend and media firmware, it has a proven concept. The chip already provided to the backend controller and normal SSD firmware in terms of error recovery, media management, the complete robust firmware already verified, and it went all the way to product qualification. So we want mainly to check, implementing the basic commands of the open channel, so that we can see the capability of the chip is compatible for all the open channel drives. This is our goal, and then what we did mainly is putting into the open channel specification 2.0 compliance, and we did basic command support for that. Also, we tested host Linux PC with PCI 3.0, and then we also tested with both, I think, as David explained, SPDK platform. It looks pretty stable, and then we also, the open channel Linux kernel also validated for several days, and maybe more than weeks, so it run well. So mainly to do this work, we also did a kind of changes in Linux kernel, because the default Linux kernel is not so compatible with all the commands what we want. So we extended that, and in fact, we also support to read, write, and erase. Even, in fact, we could run the GC operations of the OC in this drive for several days. And then, of course, the standard architecture is like, of course, Linux physical block architecture, so that the driver can access directly as a physical block, and all operations can be done directly. So these are the simple basic commands. What we have supported is read, write, or erase. Of course, read is just like any other NVMe read chunk, and then write is write chunk, like it's 96K operations for one word line. Read can be any 4K or multiples of 4K. Erase we call as a reset in open channel. Reset chunk is, you can send list of the reset chunks and then even single one. That's what we are looking for the next level, even asynchronous for the next kind of product. So get geometry is as I mentioned last slide, get geometry helps to get the application read all the geometry of the complete your drive so that it knows how many parallel units are there to perform it. And it can isolate, it can separate each parallel unit for their purpose. Get chunk information this is one of the important feature which is required for most of these open channel and SPDK purposes. Even the application customize the I/O isolation, you need to have information about media. So each physical block PE cycles are limited. So, and then also the error recovery information also is very important because once you reach a little bit end of the block stage, end of the life stage, so it's prone to more errors. So this command helps to get what is the current threshold and how much is the data prone to that, how much error prone to that, how many times is error recovery happened, all this information. It's nothing but in usual SSD, whatever counters we maintain for each physical block. And each virtual block, we maintain the information about so that we know what's the current state of each physical block and in a virtual block. So this is the get chunk information helps to read all this information from the drive so that the application can decide when it wants to do the recycle in terms of GC and wear leveling, all these things. Media feedback is mainly to give some kind of additional metadata information and all this media-related additional information. So this is the performance, what we can get from the OC current prototype. It's not full performance, but it's still a quick prototype because we did not optimize to the complete path because we want to check, mainly our purpose is to check the compliance for the chip and our firmware for the interface part. So, but we do see that theoretically it can go to the maximum chip performance. In fact, it can give the better performance, better I/O determinants than the traditional SSD. So the future purpose is like, we would like, I think if you guys have seen in case OC spec, it's a very simple spec. It has maybe maximum like all together, maybe 10, 15 commands. This is single commands and vector commands. The vector commands is nothing but you give a bunch of reads to the drive. It's like you can give like 100 reads or 100K, whatever, list of the reads. So it can perform all the commands together at a time and post the response. Same for the write. So the vector I/O operations read and write helps to give the bunch of read and writes at the same time and erases so that drive can do all the operations at the same time and you don't need to have responses for each one. This is the main purpose of vector and asynchronous. So I think that's our next step. We implement this vector asynchronous and so that we can demonstrate the high performance and full chip performance. Non-error recovery, and this is one of the most important things where, even though we do the isolation and determinism very well, still it's very important to having the very good error mechanism because eventually non-prone to errors depends on your conditions, thermal conditions and temperature conditions and power consumption limitations. All these things will lead to a lot of errors. And also end of the life, the more it goes to the number of P cycles, it's prone to more errors. So it's important to have in firmware and hardware capability to support error recovery. It's just not only firmware, even hardware need a lot of features to make all the errors can be recovered. It could be retry and several soft decodings and hard decodings mechanisms. So then all the way to RAID, we need all the steps to be done. And then the current chip, Marvel chip and firmware, we have tested very good enough for several products and it qualified for several products also. Meta support, and we also would like to store this meta information into the NAND so that host can know that the relation to where the actual data and what is the LBS so that it can do the more advanced operations. This also we are trying to do it in the future. And then performance tuning, of course, yeah, it has a lot of scope to tune further to demonstrate. But anyhow, still open channel specification is kind of draft, and then it has to go to the more maturity to handle the several conditions. We need to look into that more in down the time. To summarize, our controller is capable of our 88SS108 controller. We use as a conventional conventional SSD, and also we can use for open channel SSD because we evaluated theoretically and also the prototype what we have seen with SPDK demo and also earlier demos. It's compatible to use as an open channel for our cloud market. And we do have a very highly efficient reusable components to spin off if based on customer needs. We do have different layer components where we reuse. So we have a unified HAL. It's like if customer can reuse all our hardware access using very easily with this HAL interface, and then we do have an exciser for each HAL API. So once we have this software, the entire hardware is excised, so the customer can access whatever in their firmware, whatever features in the hardware. That's what I think easily integratable. So we do have full feature media management and error recovery firmware. So that allows us, very good capable of handling all the net errors and media management. So eventually, the media management is mandatory piece even if you go to the cloud market like SPDK and the open channel for, even we expose all our parallel units to the top level, we still need to do this error recovery very efficiently. So we do that very well, and also we have firmware for all IP blocks. So this about from our side, my side, and then I would like to keep some time for question and answers for together. Maybe David, you would like to join? Yeah. So we. Any questions? Yeah.
With SSDs, whether they're conventional ones or open channel ones, on a per IOP basis, metadata, small pieces of metadata need to be made durable on a per IOP basis. With the open channel approach, does the need to commit those small pieces of metadata to durability, does that end up being in the critical path from a latency or throughput perspective? And how is that addressed?
Okay, so that's a good question. So the two kind of meta we talk about, I think, in my understanding, the metadata which is required to manage the media firmware still has to be stored in the NAND. Similar to, I think, the conventional SSD will have the more larger chunk of the metadata because you do have flash translation layer inside your device. So you will have the more quantity of the metadata. Here, the metadata quantity will be reduced because we don't have the conventional FTL here, but still you need to have this metadata to manage our media information and still has to be stored. And of course, this has to be there, but I think the latency wise, we need to isolate so that we can still geometry wise what we expose to the user side and what we don't expose can have the metadata. So you can have the separation between metadata and for the user data to reduce the latency and the noisy effect.
Thank you.
Yeah. Any other question?
Okay.
Okay.
Thank you.
So thank you so much.
All right. Thank you.
Yeah.